Hello, everyone. It's my pleasure to welcome you to the next installment of our eSymposium series, where we present expert users and members of our community who will give you presentations on key topics of interest to a wide range of people. Today, our presenter is Dr. Jacob Apkarian, founder and CTO of Quanser. More about him later, but first I want to give you a few housekeeping bits of information. During the course of this seminar, if you do have any questions, we do have mechanisms for you to ask them. Right now, all of your phone lines are muted so that we don't get background noise to interfere with the presentation. But you do have access to chat facilities or messaging, text messaging, which is on the right-hand bottom side of your screen, and you can use that to type in your questions and send it to us. If it's of an urgent nature, like you're having technical problems, we'll answer that immediately by text. Otherwise, what we will do is hold your questions. If it's more on the contents of the presentation, we will hold it till the Q&A session following the main part of the seminar. With that, I want to offer just a few brief comments about what you are going to see today. The title of the talk is Rapid Prototyping of Advanced Mechatronic Systems, and this is a fairly pertinent topic these days, as many of you may be aware. And so we've seen a tremendous growth in interest in topics like this, and that's one of the reasons why I invited Dr. Apkarian to our seminar. So a little biography of Dr. Apkarian. He's the founder and CTO of Quanser Incorporated, and he has taken the company from a startup to global leadership in the development of a wide range of real-time control systems and services for industry and research. And today, as Quanser's Chief Technology Officer, Dr. Apkarian is responsible for the company's technology as well as its overall R&D direction. Before launching Quanser, he held positions as Robotics and Assistive Devices Director at Lyndhurst Hospital, and as well as a senior engineer at Spar Aerospace, where he contributed to the development of several key projects, including control systems for the Canada Space Arm as part of the Space Shuttle program and now the space station, and as well as other components of the space station. Prior to that, Dr. Apkarian was also spent time as a professor in electrical engineering at the renowned University of British Columbia. So with that, I would like to formally introduce to you Dr. Jacob Apkarian of Quanser. Jacob?
Good afternoon, everybody. Tom, can you hear me?
Yes, I can.
Okay, thanks. Well, thank you for joining me in this rather informal presentation, I'm calling it. I'm going to be talking generally about this concept of rapid prototyping of mechatronic systems. So really this presentation is more of a technology overview of how mechatronic design and implementation could be performed using existing rapid prototyping computer-aided design tools. Before I start the presentation, I'd like to talk more generally about what is mechatronics. I'm not sure if the audience is familiar with the term or not, so I'll just give a quick definition of what mechatronics is. If you look on the web, you'll find all kinds of definitions for the term and this famous diagram that you see on the right here. So mechatronics involves the harmonized design and development of complex systems, taking into account the interplay of the various engineering domains that contribute to the entire system. So you don't just design a mechanical system, you don't just design an electrical system, you kind of look at the system as a whole and design from the bottom up, taking into consideration all the elements involved that will eventually, comprise the system. In the traditional design approach, and I'm talking traditional, maybe in the last 10 years things have started changing, but traditionally, and I'm looking only at two domains for now, and this can stretch out to a variety of domains, not necessarily just the mechanical and the electrical design domain, but it could be anything from aerospace to chemical. Engineers typically design, the core of the system, the mechanical design. They might do some simulations as the tools are available, and also they design the electrical system. There's always interplay between the electrical and the mechanical design, which are based on system requirements and specifications. And simulations are run independently. The mechanical system is simulated without taking into account the electrical characteristics of the system, or vice versa. The electrical design is performed using, the CAD tools that are readily available and simulated. And then eventually, typically they approach the control engineer and they say, well, here it is, we built it, now control it. So mechanical design is done by itself, electrical design is done by itself. Eventually, a control engineer is brought in and they're asked to control the system. And the control engineer will run some simulations based on the system that's passed on to them. And as time goes on and simulations are showing, potential performance, then the system is constructed and integrated. And as the system integration proceeds, there are more and more simulations and control design issues that are encountered. So typically, you go back and start looking at the control system given the mechanical and the electrical system that you've constructed. Unfortunately, sometimes it doesn't work out, so you end up having to go back to the drawing table and doing some mechanical design and electrical design given the lessons that you learned from the system integration. We try to avoid those steps, try to do things more this way. But again, the system is not designed holistically. Parallel paths are taken, and eventually they're intersecting at the integration of the system. Mechatronics, however, tries to approach the entire design in a holistic way. Holistic meaning taking into account the entire system with all its components. So not separate designs, but all designs are performed synergistically. And while one is looking at the electrical characteristics of some part of the system, they are also considering how this is going to integrate with the mechanical system, what controls are required, what kind of computer characteristics are required, what power requirements are required. They're all kind of taken into account all together with constant interaction between the teams that are responsible for different domains in the system. So in the mechatronic approach, you don't just do the parallel design of the mechanical and the electrical in this case. You would also take into account the control system, which as the design is progressing, the control is always feeding back into the mechanical and the electrical design, specifying constraints and capabilities of the system, as well as the constraints that are imposed by, let's say, the computation capability of the computer that's going to be used. And then the simulations would not be run just in one domain, they would be run in multi-domains. So you'd have a simulated system that incorporates all the domains into one simulation. Now that could result in a very complex system requiring a lot of computational power. However, you may simplify, the simulations to incorporate just black box responses, but at any rate, you're always doing a multi-domain simulation, not ignoring, one component while doing a design. And that multi-domain simulation can result in, reviewing the mechanical design, the electrical design, and the control design. And once these changes are done, they should be automatically integrated into the multi-domain simulation and proceed from there. Once you're comfortable with the multi-domain simulation, if you can, you should also perform some hardware-in-the-loop simulations, taking into account some of the hardware that's already constructed, not necessarily in the same time scale. And 3D animations are always helpful, so the multi-domain simulation would be running a 3D animation of a mechanical system if there is one. If it's purely electrical, then you can't do 3D animations. But 3D animations are very useful in visualizing what the performance of the system is in real time and changing parameters in hardware-in-the-loop simulations and observing, characteristics and behavioral changes. As the simulations become more complete and satisfactory, then one would move on to constructing the mechanical system and then integrating that mechanical system into the hardware-in-the-loop simulation. Ideally, the hardware-in-the-loop simulation would end up as the actual deployed system. So as you're developing hardware, you're also developing the deployed system. It could be an embedded system. You might be developing a hardware-in-the-loop simulation with the actual embedded controller. As the hardware-loop simulation progresses, you might be tuning the control design, but really avoiding these last two dotted lines that take you back to the mechanical design and the electrical design. So in concept, I'd like to look at what rapid prototyping means and how this relates to the Mechatronic approach. Rapid prototyping is the common definition. If you look up on the web, you'll find definitions for rapid prototyping. Wikipedia is we're all becoming wikidemics. You can look at Wikipedia and find out that rapid prototyping means the automatic construction of physical objects using solid freeform fabrication techniques. There are many products on the market that will take a Solidworks drawing and from a Solidworks drawing manage to make a physical object that is as close as possible to that Solidworks drawing that you had designed, and therefore use that for prototyping. But that is only physical prototyping. I'd like to extend that definition by introducing this new term, Mechatronic Rapid Prototyping. I'm extending the definition of rapid prototyping such that it encompasses the holistic design and construction of mechatronic systems using synergistic and integrated computer-aided design tools, such as automated mathematical modeling, real-time animated graphical simulations, automatic code generation, and hardware-in-the-loop testing. So the ideal mechatronic would start with a concept which covers all domains. Let's say you want to design something, then you figure out what domains you're working in, and you start with a very general concept in all domains, taking into account the interplay between them. And as you're developing, you're also developing a modeling and simulation in all the domains that are involved. And those feed back into each other until you have a concept that you're comfortable with. As the concept develops, then you start performing some hardware-in-the-loop simulations before you do any kind of construction. And from that, you loop back to the concept, which might require some design changes in some of the domains. But as soon as you make a change in one of the domains, that automatically should reflect into the multi-domain simulation. So any change done in any of the domains is always upgraded in the entire simulation paradigm. As the hardware-in-the-loop progresses, then you can start using rapid construction techniques, some of which could be the physical prototyping methods I described earlier. Along with that, you can use rapid construction of circuit boards or any other, outsourcing that can rapidly construct parts for you. Some of things you cannot make in-house, cannot use rapid prototyping techniques to use. You might have to do things, in faster ways, but not in the traditional way. Like you avoid, injection molding by using rapid construction, using SLA or 3D printing techniques. You can also avoid large runs of circuit boards by going to rapid board manufacturers and assemblers. And that loop closes back into hardware in the loop. As you construct the system in components, you might eventually build up the entire system using rapid construction techniques, and then you're done. Hopefully, you can also develop some 3D animations at the same time. So before you do any rapid construction, you are getting a better feel of the system using 3D animation that are run directly from the multi-domain simulation and the hardware in the loop. So are we there yet? Can we really do this kind of approach? Well, all the tools are there, and we're striving as time goes on to develop a method that would lead us into this rapid scheme of developing mechatronic systems. So the tools are there, but they're not synergistic or integrated. I'd like to define those terms. Synergistic, by synergistic I mean the interaction of two or more CAD tools such that their combined effect is greater than just the sum of their individual effects. So you might have a mathematical modeling tool, and you might have a 3D, solid modeling tool, but by themselves they're great, and each one individually, when used, can save you a lot of time. But when you actually combine the two together, you might actually get a tenfold improvement in productivity and in error-free performance than you would if you used one individually and then the other one sequentially. And by integrated, I mean organized or structured so that the CAD tools function together seamlessly. I don't want to use one package and then now move to the other package and launch some other kind of interface and have a complicated way of connecting the two together. I'd like to do this seamlessly without manual or programmer intervention. I'm talking about a wish list here. I'm not saying this is done. This is how I'd like to see things moving so that we can move into a rapid prototyping environment for mechatronic systems. The tools that are there, we use a lot of these tools at Quanser. For mechanical, we're using Solidworks. For electronics, we're using CADStar. There are many other systems, out there that perform the same type of work as Solidworks and CADStar. For modeling and symbolic math, we've been using Maple for close to 18 years now, and Maple meets our needs for symbolic math and simulation quite well. Design and simulation, we use MATLAB and Simulink regularly and consistently, and we've integrated MATLAB and Simulink seamlessly with a hardware-in-the-loop development system called Quark. Quark is developed by Quanser and supports code generation from Simulink to run real-time code and perform hardware-in-the-loop testing as well as deployment. For animation, we are using OpenGL, and sometimes when it's too difficult to actually develop the dynamical equations of a system, we have looked at PhysX engine to solve some of the, not solve, but actually give us, dynamic performance in simulation mode only for some dynamical systems. I'm going to go through some examples on how we have attempted to use this rapid prototyping approach for mechatronic systems using three different, applications that we've worked on in the last few years. The first one is a handwriting reproduction robot. So the goal of this project was to develop a robot that will reproduce signatures from a remote tablet. So very simply put, you have a remote PC, the user has got a tablet that he can write on, and whenever they write, you want a robot at the far end, could be anywhere in the world, to reproduce the handwriting in real time. In real time meaning, as soon as possible, given the time delays in the network. This is not a simple task. Reproducing handwriting has a lot of high-frequency components, requires a very robust mechanical system, and accuracy is important. The goal was to reproduce signatures that will pass the scrutiny of forensic scientists examining signatures, produced from the robot versus real signatures. So we started by a concept design using SolidWorks. You see here a SolidWorks drawing that's been rendered. The design is a 2DOF pantograph system driven by DC motors. It's a 2DOF robot with not so simple kinematics because it's a closed kinematic chain, and the dynamics are not that simple to derive either. So when we want to derive the mathematical models for this thing, we rely on Maple heavily. With Maple, we start from the basic principles, defining transformation matrices, as well as Lagrangians and dynamics to develop the differential equations. Once we have entered all this in Maple, we have a systematic way of going through the equations, letting Maple solve a large chunk of the equations, thus producing error-free differential equations and kinematic transformations, and converting these into C programs using the code generation capabilities of Maple. Once we do that, then we can develop a simulation of the system using the Maple code generation and embed that into Simulink S functions. As you see here, I have a section of code that was derived from that code generation section of Maple. You can recognize, anybody who's using Maple code generation can know their temporary variables, T3, T5, T6, T8, etc. So we embed that all into a Simulink S function, which will now run in real time using Quark, and we can run real-time simulations on the system without actually building it in any way. We did not attach this to any graphics in this case because it was only a 2 degree of freedom system. We were able to monitor the X and Y motions using simple XY plots. And we were able to tune the system, and from SolidWorks, we can also get all the mechanical characteristics of the system, like joint center of mass, inertia, masses, embed that all into the code-generated functions. And the nice thing with the code generation, they can all be parameterized. So it's not a differential equation for which you have no control over the variables. You can actually individually change variables on the fly, right from the simulation, or observe the changes in the system dynamics as you are changing specific parameters. The control system is eventually then designed using MATLAB and Simulink. You see here an entire Simulink diagram that has embedded a variety of functions, including data acquisition blocks, motor simulation blocks, system dynamics blocks, and kinematics blocks derived from Maple embedded into S functions. And finally, the system is constructed using some rapid prototyping techniques, I'm pointing with my mouse pointer here. The arrow points at all the parts that were constructed using a 3D printer. So all of these crucial components, links, arms, joints, lifter, motor mountings, all of this is built in plastic using rapid prototyping techniques. So you draw it in Solidworks and send it to a printer, and out comes the part, and you can assemble it. And again, this gives you the capability of changing parts on the fly and doing design changes very quickly. If you need some other parts cut, there are other methods of moving diagrams to local water jet cutters or laser cutters, so you can get some precision parts made very quickly and rather inexpensively. Following the construction, we integrate the whole thing using a hardware loop integration software called Quark. We also needed to run this thing remotely using a communications package, and Quark also embeds communication toolboxes that support a variety of communication schemes such as TCP/IP, UDP, or serial. So we were able to run this robot remotely and control it via this diagram without writing a single line of code eventually, by just integrating Maple generated code into S functions and using all the standard Simulink and Quark libraries to control the system. So really not a single line of code was written here to get this thing up and running. And that was again done using Quark. So the process, just to describe the process, in general, how this was done in a Mechatronics approach using rapid prototyping, was we started with SolidWorks. And unfortunately, through a complex, and manual process, we had to take the SolidWorks system and convert it into a kinematic and dynamic system and code that into Maple. But once that was done, then from Maple we were able to generate code for the system dynamics and the kinematics, embed that into Simulink, and then run some simulations and iterate the design before we built anything. Once we were comfortable with the design, then we started printing parts and constructing the system. And that process is automated. It's a simple printer, essentially, that you take from SolidWorks, click print, and you printed the parts. Construction is manual. You cannot avoid that. We're not looking at large production runs. We're not going to automate the construction process. After all, it is called rapid prototyping, so that's okay to use some manual construction, and the integration is manual. However, going from a simulation to a real-time control system is also automatic. We take Simulink diagrams, use real-time workshop, generate real-time code that runs with the aid of Quark, as well as the real-time communications package. The entire thing is then iterated through Quark and Simulink once it's constructed. And if there's any minor changes, you can reiterate through SolidWorks and print some new parts. For example, we had designed a voice coil actuator to control the pen mechanism. We eventually opted to use a more off-the-shelf motor to do the pen lift, and then we had to iterate that design. But that was not a major design change. These are minor design changes we were able to redo again through a mostly automated process. And eventually we deploy it, and since Quark can actually be deployed, the code that's generated from Simulink can now be deployed into a standalone headless system that does not need Simulink, MATLAB, or Maple, or anything else, just the operating system and the code that was generated, and run a real-time system and perform signatures remotely using this robot. So this is one example where we used what I'm calling a rapid mechatronic prototyping system. Another one was a purely electrical design. We were asked to design a high bandwidth linear current control amplifier. And in this case, we start with CADStar, which is our in-house design tool for designing electric boards and laying out electric circuits. However, when you run a simulation for electrical systems, you cannot really change mechanical parameters. If you want to drive a motor with this amplifier and you want to be able to change the inertia of the motor or the inertia of the load, or introduce some backlash into the dynamics, that cannot be done using just CADStar or any other electrical simulation package. So what we did, we developed a mathematical model that incorporates loads and inertia parameters right into Maple and developed the differential equations accordingly, and then moved that into MATLAB and developed a simulation in MATLAB in order to design the parameters, again, parameterized simulations, not just black box simulations. So you can change every variable in the design and observe its effect on the actual response of the system directly from the differential equations that are derived from Maple. And then, again, simulate the system, embed the code that's generated from Maple into S functions, perform a full design on the system. For example, attain ideal step responses and frequency responses. Real-time simulations look at time responses and transients, saturation effects, nonlinear effects, loading effects, variations in load parameters. All of that is done from code that's been generated from Maple and embedded into MATLAB and Simulink and run in real time using Quark. If the simulation requires non-real-time simulations but very high sample rates, then we run it in non-real time. In this case, the simulation was non-real time when we're running with sample rates of 100 kilohertz or small step sizes for the integration. Again, we used the same stuff was also used to generate an automatic production testing system for the runs that we are making. After the rapid construction of the first few units, we went into production of these amplifiers, and we were able to use the models that were generated in order to generate a reference model and test production runs against an actual reference model. So we have a real-time system running along with a simulated system and comparing them side by side as they go through production and come up with a report. And that report is automatically created by testing the system and comparing it to expected performance variations. So the process that we use here is, again, we had our in-house design tool for the domain that we're interested in. In this case, we're using CADSTAR for electrical design. We, again, had to derive mathematical equations from using Maple, but the transition from CADSTAR to Maple was, again, manual and complex. You had to be an electrical engineer to understand how to derive these equations. You could not just drop in an electrical component and say, okay, well, let's make the differential equations that make up this whole system with all these electrical components. You have to be an electrical engineer in order to derive these equations. Once the equations are derived, then we use code generation from Maple and embed those in Simulink. Again, iterate the process, then move into manufacturing. In this case, we don't manufacture our own boards, so we outsource those to rapid board manufacturers and then integrate it. And again, through automatic code generation, generates real-time code that will test the boards and then iterate the test process and the response that we get from the boards as opposed to simulation. Following that, we deploy the system and we have a final product. The third system I'm going to describe is a remote-controlled vehicle. We've been tasked to design a remote-controlled unmanned ground vehicle. Furthermore, the vehicle not only has to be simulated, but it has to be simulated in real time, as well as we need to simulate an interactive 3D graphical simulator in order to validate control schemes before implementation of these control schemes on the vehicle. And obviously, for obvious reasons, you need to do this before you get into unstable regions of operation. So we have a mechanical design, again, performed in Solidworks. The entire system is designed in Solidworks, and we'd like to simulate the system in real time as well as animate it in real time and interact with it in real time as if we're driving the real thing. And once we're satisfied with the performance, we're going to build it and eventually drive it remotely. But before we drive it remotely, we'd like to make sure it's going to be stable and running properly. So the tools we used to develop the mathematical model for this were a little different from what we showed you in the previous two examples. The differential equations for such a system, which comprises a variety of degrees of freedom, compression of the tires, compression of the suspension system, torquers, steering, friction on the wheels, dynamic motion of the platform, accelerations, centrifugal torques, slippage, braking. There's a lot of dynamics here that are not that simple to model. So it would be nice to have, a block that says drop in the car with these properties and, let's simulate it. It's not that simple. So we opted to use something called the PhysX engine. The PhysX engine is a physics engine that is used in gaming, and it turns out that it's actually quite good for simulating dynamical systems with multi-degrees of freedom and multiple contact points. So we use the physics engine to build the simulation for the dynamics of the system and the kinematics. We also used OpenGL separately to draw up a 3D model of a mock-up of the system in an environment which has physical and dynamic properties. We drop some planks of wood and a tree, each one with different properties, and you can actually drive the simulation using a joystick. And in this case, we also have haptics incorporated, so you actually feel that you're driving the vehicle using haptics. So all the forces and the kinematics and the dynamics, however, are solved separately using the PhysX engine, and the graphics are driven separately using an OpenGL interface. However, we still want to do all of this through Simulink and Quark. So we've embedded the physics engine into a Simulink block. I'm pointing it out here with the mouse cursor. So this is a physics engine running a simulation of the vehicle. And on the right here is a visualization engine using OpenGL. This whole diagram, however, is run in real time using Simulink, code generation from Simulink, and Quark. We run the diagram at 1 kilohertz. We're able to update the physics engine at 1 kilohertz. The visualization is done at 30 hertz. So using the system, we're able to modify parameters in the vehicle before we build it, change control system parameters, change loop gains, integrators, filters, change all parameters and drive this thing in a virtual environment before we construct it. And once we construct it, we will still use the simulator in order to confirm control schemes before we actually implement them on the actual vehicle. So the process, start with Solidworks, draw up the system, move to PhysX engine, again, and move to OpenGL to do the graphics. Two completely different, environments and domains. And again, a manual and complex process to take from Solidworks to PhysX, and to OpenGL. They have different ways of thinking. Each one they're not integrated. They're not homogenized. Not one thing in PhysX is related to one thing in OpenGL. Completely unrelated. Eventually, we integrate all those into Simulink and 3D graphics. But once we've done that, then again we have a full simulation that we can iterate as well as generate code in real time and run in real time. And then we deploy. I think I missed the building part here in my slide, but it's the same sequence. So once we've done the actual simulation, we actually build the system. The picture actually is a true picture. It's not a SolidWorks rendering. That's a true picture of our UGV running remotely with real-time control sitting on it, as well as real-time control sitting remotely using the Quark communication toolbox. So from the above and a lot of the things we do, we are looking at an ideal process, and we hope eventually things will move in that direction. Design tools, you start with your design tools. I spoke about a couple here, SolidWorks and CADStar, but there are many, many design tools out there for different domains that can be used to develop your basic designs. However, there is no way of transferring that design into Maple. We'd like to see an automated way of taking our standard design tools and embedding those designs automatically into Maple. That is the most laborious part of the process, because the other stuff now has been done. We can take Maple and generate multi-domain simulations if that is done. However, the crucial thing here is we'd like to generate parameterized code generation, not just closed boxes. We'd like to access very specific parameters so that when we're doing our iterations and design, we'd like to change some parameters on the fly and see how they affect the system. Once we've done that, then we can iterate and go back to SolidWorks or CADStar and do the design change, and that will automatically reflect into the differential equations and all the simulation parameters that we're working with. Depending on the system you're designing, you'd like to see some 3D rendering which is done in real time so that your multi-domain simulation is also driving real-time graphical simulation of the system so that you have a better feel on the performance of the system as it would in the physical world. Following that, you would go to automated or outsourced manufacturing, and the process then remains the same, because after that, it is quite automated. You can go from, well, multi-domain simulation we're doing now from Simulink, but Simulink itself does not have multi-domain simulation. We're embedding the multi-domain simulation by writing our own S functions for the different domains and embedding them into Simulink, and thus creating an integrated multi-domain simulation by hand. But once that's done, then you can move into code generation and make the simulation in real time, or eventually use Quark for deploying the system. Of course, you go through the iteration steps by Quark and simulation, and then move to deployment.